Okay, this podcast is about so-called geometric sequences and series. We see several formulae here. The first is about finding the so-called nth term of a geometric sequence, and the nth term will often be considered the last term in a sequence of numbers relative to the first term, namely u sub 1, and r, the so-called common ratio, and n, of course, refers to the number of terms themselves. A sequence becomes a series, and we'll see that later, and we can find the sum of a series of n number of terms, where I'll refer to that as S sub n, and that summation formula will be a function of the first term, the common ratio r, and the number of terms n. And these two formulae are the same. If you factor a -1 out from the binomial in the numerator as well as the denominator, you'll get a cancellation of the two -1s, and you'll get this other similar version of it here. And worth noting, of course, is that r cannot be 1 because that would create division by 0. So here's our first example. So given a geometric sequence has a fifth term of 3 and a seventh term of 3/4, we need to find the first term. Here's our unknown first term, the common ratio, and the 10th term. So given we've got first, second, third, fourth term, here's our fifth term as given, sixth and seventh term. We can use this formula here, as we'll see on the next slide, where we can say, okay, if u sub 5, the fifth term is 3, well then the 3 as that fifth term is equal to the first term times some unknown common ratio of r raised to the fourth power. And then similarly, 3/4 was given as the seventh term, so hence u sub 7 is 3/4, and that would be equal to the u sub 7 of 3/4, so the first term, which is unknown, times r, the common ratio, also unknown, raised to the sixth power. So a quick fill-in of those two, of that formula relative to those two givens gives us something that looks like this. This looks like two equations, two unknowns, and that's exactly what it is. Several ways to solve it. If we divide the r to the fourth under, we're here. If we divide the r to the sixth under, we're here. And then, of course, if each of these expressions, if you will, are equal to u sub 1, the first term, they have to be equal to each other. That's how a form of the substitution method would work. So when you equate those two to each other, you could effectively cross-multiply, divide, as it turns out, by the 3r to the fourth, and that's why this form ends up looking like 4r squared is equal to 1, and then bring the 1 over. This, of course, is factorable. You might recognize that binomial as the difference between perfect squares, factors into 2r plus 1, 2r minus 1, which, when set equal to 0, gives us actually two common ratios to be mindful of. So the question is actually a little bit more sophisticated than one might realize. So if our r, which is either plus or minus 1/2, knowing that the first term would be 3 divided by, for example, r to the fourth, which of course came from this one particular choice here. So now we can plug in the plus or minus -1/2 here to actually get the first term, which is something that we were trying to find. Either the positive or the negative when raised to the fourth power gives us 1/16, and 3 divided by 1/16 is 3 times the reciprocal of 1/16, namely 48. So it looks like our first term is nicely 48. Worth noting is that we're going to have two tracks now to generate what's going on, because the r value, the common ratio, if you now take 1/2 of that, you're here, 1/2 of that is here, 1/2 of that is here, and you get the idea. However, the common ratio also could have been -1/2. 48 times -1/2 is here at -24 now. -24 times -1/2 is back to 12. So we actually generate a second sequence down here that oscillates. Why is r called the common ratio? Because in effect the way it's defined is if you take a term, in this case 24, and divide it by its previous term, you get a half. If you take the 12 and divide it by its previous term, you get a half again. 6 over 12 is a half. So you've got this common ratio threading through. So we can see that the first term lends itself, in this case, to second, third, fourth, fifth term, which was a given. Same thing here. You oscillate back and forth, but you still arrive at the 3 as a positive 3 in both cases as our fifth term. Sixth term, seventh term had to be 3/4. It still holds up. If you keep this trend going, it looks like the 10th term, which has to be our first term, which is safely 48, times r raised to the 9th power. Well, now you do have a plus minus consideration here, and you will find that the 10th term out here would either be positive 3 over 32 or negative 3 over 32, and of course both would be required. Let's shift from a pure sequence setting to a series setting. So given something like 1,000 plus 500 plus 250 plus et cetera, down to some 10th term, we're talking about, in this case, a kind of a summation. So let's firstly, before we get into the actual series, which is the addition of all of these, let's actually identify first or show that that 10th term can be written in this particular form, where P and Q are so-called values to be found, where P and Q have to come from the set of positive integers. So similarly to what I was saying previously, take the 500 divided by 1,000. That ends up being the same as the 250 divided by 500. So that confirms we have a common ratio, or an R value, of 1/2. And the formula that we need is that the nth term is equal to the first term u sub 1 times r raised to the n minus 1. So that's pretty straightforward. So the 10th term will be our first term of 1,000 times 1/2 raised to the 9th, as it turns out. And then if this were a paper 1 type setting, it's a little bit challenging, but you'd have to play out what's going on here. 1 raised to the 9th power, of course, is itself. It's just 1, and 1 times 1,000 is 1,000. And 2 raised to the 9th is a bit of a stretch to come up with the fact that it's 512. And so this reduces this fraction to 125 over 64, and it goes even further to have it be thought of in terms of 5 cubed over 4 cubed. Hence, we met the form that we were required to generate, where P is equal to 5 and Q is equal to 4. I did just throw this into the calculator, and if in fact you had a paper 2 setting here where you did have some technology, you could actually take something like the 1,000 over 512, get a decimal equivalent of it, and you do have a math fraction converter which would allow you to convert it to the 125 over 64 to ultimately get to the result of P and Q that you need. Could also be a paper 2 question. So let's now deal purely with the series itself. So let's find n such that the sum of some particular number of terms is actually greater than 1,999. You can see there's a sum here already of 1,500. You throw in 250, here's 1,750, and you get the idea at what point, which number term, which n value allows for that sum to be greater than 1,999 as you're adding in more terms. So we'll focus on this formula here. We because we're dealing with a summation now properly, and this is our summation formula for the series, the so-called series, and some unknown number of terms. The sum of that can be represented as the first term, which is 1,000 times 1 minus the r value raised to the n over 1 minus r. This is something that we can say, okay, that's going to be 1 minus 1/2 is 1/2 down there, and 1/2 divides into 1,000 2,000 times. So we have that the s sub n expression looks like this algebraically. We need to force our s sub n's to be greater than 1,999, so we need to solve this. There's a handful of ways that we can solve that, so I've got the same expression here. Actually, I think what I did was I divided the 2,000 under. We can safely divide under and say that we need this expression to be greater than 1,999 over 2,000. And so what I've done next is to say, okay, this I'll just subtract this fraction over to the other side, hence it's negative. I'll take this fraction, which is negative, and I'll add it across. And so 1 minus this fraction is really 2,000 over 2,000 minus that, hence the 1 over 2,000. So if I stop here for a second, before we go further with a kind of a paper 1 approach, let's take a look at this from the perspective of a paper 2. What is this trying to say? This is trying to say, when does this 1 over 2,000 function exceed this exponential function? Well, y equaling 1/2 raised to the power, namely this right-hand side, that's in red here. So that's dropping down as this exponential decay function. And the blue, which is y equals 1 over 2,000, that's just a straight line, admittedly quite a small number. It's just a constant function. And there does come a point where this exponential function is less than the linear blue function. And where that point is right here. You could use your intersection feature to establish that they intersect at around 10.96. Hence, you need to go past that to 11 in order for the red graph to be below the blue graph. So that's a valid paper 2 solution if you do a quick sketch by way of your method. A paper 1 challenge would be the classic way to get an unknown up in a denominator. To swing it down is to apply logs to both sides. And when you apply logs to both sides, in this case I chose natural log instead of log base 10. It's more common than natural log, especially on IB papers. The n swings down, that's a logarithmic rule. What's a little bit slippery is if you now divide the ln of 1/2 under, you'll notice that this went from n being less than that to n being greater than that, and that's because if you checked out on your GDC, the ln of 1/2 is actually negative, and when you divide across an inequality by a negative, you have to reverse the so-called sense of the inequality. Hence, n has to be greater than whatever this is, which ends up, not surprisingly, being the same value you see here, and you still conclude that n is equal to 11.